Hi everybody, welcome to the lecture on downstream processing in biotechnology. This lecture is the last section of the membrane filtration, which we will consider on the dialysis. Dialysis is one of the membrane filtration in a specific case. Mostly we use the dialysis to for the artificial kidney, that's like for the purify the blood or separate some uric acid, urea from the blood. Okay, they mainly use the separating macromolecule from smaller molecule. In the feed, this is the feed side. This for this feed side. This is the permeate side. The feed side contains solvent, contains source A, source B. For this case, the source A is mostly passed to the membrane, and source B is hard to pass to the membrane, and colloid also is cannot pass to the membrane. We can use it to separate the source, a mixture source, right? We can use separate to source A. Source B also pass to the membrane is a slow dialysis. For the fast dialysis is source A. And then we have the sweep liquid or some liquid to pass to carry the solute in the diffusion liquid or diffusate. We call it diffusate. We use the liquid to sweep this we or solvent toward the side toward the permeate. Okay, the membrane is maybe thin and so use high A can pass to by concentration by driving force. Previously, right, microfiltration, out of filtration, the driving force is pressure. But for the dialysis, the driving force that you can drive. So use A also G, so use B pass to the membrane is the concentration driving force. Because the concentration of solute A is higher in the feed side, and then it can diffuse from the higher concentration to the lower concentration, Okay. From this figure, we can see that only solute A can pass through the membrane with a faster diffusion. But solute B also, but it's lower diffusion. We can separate solute A and solute B from this case. And also we have the pressure to dry, some pressure to dry P1 and P2 to dry the solute liquid. The colloid for the colloid does not pass through the membrane for this case. With the pressure is P1 equal to P2. The solvent may be also passed through the membrane, but by a concentration having force acting in opposite direction. What does it mean? The solvent in the sweep liquid or diffusate and in the feed, because the solvent at this side is higher than this side. Okay, solvent can diffuse to the membrane in the opposite by the osmotic pressure. Osmotic pressure is the more osmotic pressure that's right from the lower concentration of solute to the higher concentration of solute or the pure solvent to the solution, thing like this is the osmotic pressure. You have the reverse osmosis process that we can dry from the higher solute concentration to the lower concentration, something like this. But we write solvent, not solute. Okay. The application of dialysis include we can remove acid or alkaline from product. We can remove salt or low molecular weight compound from the solution of macromolecule. We concentrate of macromolecule, or we can use the hemodialysis. Hemodialysis, we can use this to purify the blood, or we can use this membrane to separate uric acid, to separate urea or another inclusion body, and then you get pure the clean blood for that case. Okay, if we look at this model, we have the membrane and we have the concentration in this side. We have the concentration of upstream. We have this is the film around the membrane. This is the bulk concentration. That's mass transfer to the membrane, and then it's surface of membrane and diffuse across the membrane and diffuse across the film around the membrane. This is the bulk concentration of downstream. The concentration difference of the solute across the membrane is driven by the Fick law of diffusion. J equal to S D E F delta C divided by delta M. S is the dimensionless solute partition coefficient. D is the effective diffusivity of solute within the membrane, or effective diffusion inside the pore in the membrane. Delta M is the thickness of the membrane. The thickness of the membrane. Delta C is the concentration difference between downstream and upstream side. Okay, for this case, you can combine the membrane mass transfer coefficient as shown by J is equal Km delta C, or equal to delta C divided by Rm. Km is mass transfer coefficient. Rm is mass transfer resistance. Mass transfer resistance. For this case, we can assume Km and Rm is constant for a particular solute membrane system. This constant is independent of operating parameters such as hydrodynamic condition outside the membrane. Diuresis involve the flowing of liquid on the both sides of membrane. This is indicate the membrane resistance alone syndrome govern the solute mass transport. And the liquid boundary layer either side is both sides of membrane also contribute the resistance solute transport. That means what does it mean? We have the resistance due to the membrane itself because it's Rm, and also the film or boundary layer in downstream side and upstream side also the resistance to the mass transfer. If we would like to increase the mass transfer, you can reduce the thickness of boundary layer. The thickness of boundary layer, we get the flow is turbulent or the good flow or good mixing. We can reduce this resistance. We can reduce resistance. If you would like to reduce the membrane itself, okay, you can use the membrane with good property or selectively to diffusion of some solute across this membrane. And also from this slide, we have three terms of resistance of the mass transfer across the membrane. That's right. The film for upstream, the film downstream, and membrane itself, we can represent by the total resistance by RO equal to R1, Rm, and R2. RO is the overall resistance. 1 is the resistance for upstream. R2 is the resistance to downstream. And also, similarly, you can correlate the KO is the overall mass transfer coefficient in terms of K1, Km, and K2. Upstream side for K1, downstream side for K2. Km is the mass transfer coefficient due to the membrane cell. And then you can correlate the mass transfer or mass flux from the mass transfer. That's the mass flux equal to KO equal to C1 minus CO. C1 is the solute concentration of the feed. C2 is the diacid concentration. Concentration after the some solute diffuse to the membrane. K is overall mass transfer coefficient. Like this. And if we operate the membrane in the hollow fiber, the side is a hollow fiber. We have the feed inside tube and product inside tube, and also we have the diuretic fluid like some sweat liquid flow in this and out at diuretic. At diuretic, that means the fluid includes some solute diffuse to this and product, and also the some feed include solvent or include diuretic fluid. Okay, you can use the log mean temperature log mean temperature or log mean concentration is the same you study in heat exchanger. For log mean concentration, it delta Cm is the difference in this location and in this location. Is delta C in this location C1 minus C3 minus delta C in this location is C2 minus C4. Delta log mean is divided by log delta this side and delta this side. You can use the delta log mean for that case. This is for the driving force in hollow fiber membrane expressed in terms of log mean temperature. It's the same. It is the same but different. This is for the co-current. The flow is parallel. Feed in this direction. Direction feed is also in this direction. But for this case, it's the counter current. Feed in this direction. Directing in opposite direction. Okay. We can calculate the delta T log mean. The delta T log mean is the delta C it only depend on the location. Previously, we had C1 minus CT, but for this C1 minus C4, C2 minus C3, something like this. This is for the operation is concurrent or countercurrent. Concurrent is the flow in the same direction. Countercurrent is the flow in opposite direction. Mostly in the operation, the countercurrent dialysis is the most common in the optimum operation. The advantage of countercurrent is a more uniform concentration gradient like this. This is for the countercurrent. And can be maintained along the length. For countercurrent, if you plot between the concentration and the length, the free side concentration is dropped if we consider the free side, or if the product in the free side concentration is increased, the dialysis concentration is dropped. Something like it depends on what concentration. If the product in the free side, okay, concentration is increased and dialysis is decreased. And if we talk about the concentration profile for co-countercurrent, it's not uniform. It's not uniform. This is the free side. This is the dialysis. This increase, this decrease by this. Okay, for the last example for membrane operation, for the below figure show the completely mixed dialyzer unit, plasma having a glutamine concentration of 2 kg per cubic meter. In this plasma include glutamine. Glutamine is some amino acid. Is pumped into the dialyzer. In the dialyzer, we have mixer, that's an impeller to mix to drive in the concentration to pass through the membrane. This is the membrane, some membrane. For this case, we have the water flow parallel to the plasma with the rate of this value. The water is the dialysing fluid. And also we know the overall mass transfer coefficient is this value. The membrane area is 0.05 square meter. The question is calculate the steady state concentration of glutamine in the product and dialysis system. What is the glutamine in the product? We feed plasma with the glutamine in this. And also what is the concentration in dialysis. For this case, the objective, we would like to separate some solvent from plasma into the water, into the water and the product included in the plasma itself. Assume that there is no convective transport through the membrane because the membrane is for it's very small size. If we consider this only diffusion compared to the convection. Convection is the mass is driven by the flow, but the flow in pore is quite slow compared to the diffusion. Okay, we can cancel the effect of the convection inside the pore or inside the membrane. Okay, in the model, we have the plasma. F1 is the flow of plasma. C1 is the concentration of glutamine in plasma. C2 is the concentration of glutamine in the outlets of plasma. And C3 is the concentration of glutamine feed with water, which is zero. For this case, we feed pure water. C4 is the dialysis concentration. For well mixed concentration, C4 is equal to output concentration. C2 is also output concentration. This is based on the well mix because we have a mixer impeller inside. Okay. And then we consider the steady state overall material balance for glutamine. That means we balance on glutamine for overall system. For this case, there is no concentration or there is no the generation of consumption term. They have no new chemical, new substance. There is no reaction. And also we feed in, feed out continuously. We can cancel accumulation term with a steady state. Input equal to output. The input term we have F1, F is flow rate. It's volume per time. C is mass or mole per time. You get mass or mole per time. C is mass or mole per volume. F1 multiplied C1 is equal to mass or mole per time. Plus F2 C3. Because C3 is 0. We get F1 C1 equal to output. Output F2 C4 plus F1 C2. Like this. And also if you require the mass transfer expression, N equal to K or C2 minus C4 equal to C2 minus C4. This is the mass transfer rate. Mass transfer rate. The amount of glutamine living with a dialysis should be equal to the product of the flux area. This is the F2C4 equal to Ka multiply a C2 minus C4. C2 minus C4. C2 minus C4. And then you substitute the known value into equation 1, this equation, and equation 3. And equation 3, you substitute this equation and this equation. You get C2. That's right. Unknown is C2 and C4 because you know C1 and C3. The C3 is 0. You know C1 is the feed concentration. Feed concentration. 2 kilogram per cubic meter. This is the feed concentration. You need a folate F2. That's right. This is the folate. This is the F1. And this is the F2. You know this F3, sorry. This F3, this F1. That's right. You know F2. Okay, you know F1, sorry. You substitute F2. For this, you don't know C2 and C4. Okay, from the equation 1, you get this, and from equation 3, you get this. So you substitute in this, you substitute C1, F1, C1, F1, C2, F2, C4 is unknown. Sorry, F2 is known, C4 is unknown in this case. Okay, C2 is unknown. You get this equation. And then you substitute all unknown value into this equation, equation 3. F2 you know, C4 is unknown. KO, A you know, KO, A you know. C2 and C4 is unknown. You get two equations. You can solve this simultaneously because you have two equations and two unknown, C2 and C4. You can solve this by manual or by program. And the last you get the concentration of C2 and C4 in this term. C2 is equal to 1.028 kilogram per cubic meter. C4 is 0.541. Look at this. C1 and C2. The C1 is 2 kilogram per cubic meter. 2 kilogram per cubic meter. And then you get C2 is 1.025 kilogram per cubic meter. This reduced because some solute is diffused across the membrane to the other side. The concentration of C3 is 0, and C4 is the concentration is the water side is increased because some solute diffuse to the membrane and some water diffuse across the membrane to the plasma side, something like this. Okay, this is all of the membrane that I talked to you. In conclusion for the membrane operation, in the first, we talk about the kind of the membrane like microfiltration, ultrafiltration, hot flow, or cold flow filtration, or dense filtration. And also we talk about the dialysis filtration, reverse osmosis. And then we talk about the property of the membrane, what kind of bacteria we use to produce the membrane. We talk about the latent property. And then we talk about equipment, right? Equipment for concentration, for fractionation, for the filtration. And also we talk about the lecture on the configuration batch, phase batch, continuous operation, and multi-step operation. And the last topic we consider the dialysis. I think it is covered for the membrane application in bioprocessing. Okay, thanks for your cooperation. Okay, I will stop the lecture on the membrane in this slide. Thank you.